Hello, in this video we're going to be proving some Boolean expressions using Boolean algebra properties. So for example, x plus x and y equal x, or x or x and y is equal x. And this is a new property called absorption property. So to prove this, I'm going to start with the left hand side. So what I could do is use the identity property. So instead of x, I'll make it s dot 1 plus x dot y. So what I used is 4b. And the reason why is that I could see that if I use distribution after this, I will have y or 1, and that will give me just 1, and therefore I will stay with just x. I always keep in mind my destination, what I need to prove. I need to get to just x. So how to get here? We have x dot 1 plus x dot y using the distribution property, which is 3b. We end up here, and what I could do is commutative property, y plus 1, which is 1a. And now after this is basically just 1, so I end up with x dot 1, and because of universal bound. And we know that x and 1 is just x, again the identity property. And we are done. So we went from one side to the other. Well, the second one, as you see, this is a plus, become that, and a dot become plus. So I don't need to do the proof again. So all what we could say is that x dot x plus y equal x is true by duality. Meaning I could just rewrite the proof again, but instead of a dot, I put a plus, and a plus is a dot, but instead of 4b, I call it 4a. 3a, 1b, universal bound, and 4a, and it will give me exactly the same thing. So no need to rewrite the proof. We just say it is true by duality. And this is the same with the following. As long as you see, you prove one, and the other one you're going to say it's true by duality. So for this example, what we have is x dot y plus x dot z is the same as x dot y plus x dot z. So we start with one side, and I'm going to start with the left hand side. So I see that if I use distribution property, because I need x dot y, so at least I'll get there for this first term, plus, and then x dot z. So what I'm using is 3b, distribution. And now we'll leave that first term the way it is, but the next term I'm going to use again distribution property. So what I would use is associative property. I just move this parentheses in the first, so we'd use 2b. And we know that x dot x, that's the idempotent. This is just x. Same power. And I'll stop right here because that's what I want to get into. Very simple. So what I would say, x plus y dot x plus z, it is equal to x plus y dot x plus z is true by duality. The next example, what we have is to prove that x or y, that x naught or y is equal to y. So we need to go from all of this to y. So I could use the commutative property, that means put the y first, which is 1a. And the next thing I will use the distributive property, but this looks different than the algebra distribution property because it's a y plus and then x dot x naught. So what I'm using is 3a here. Please review the properties if you have any issues with one from this step to this step. And now this is basically 0 complement 5b and identity, which is 4b, 4a, because it's a plus, so it's a. And the other expression is true by duality. Similarly, we'll follow. So I'm going to go from the left hand side. Then every time I have the parentheses and negation outside, I think of De Morgan. Just to remind you, when we did set theory, De Morgan's law was A union B naught is the same as A naught and B naught. The same as A and B quantity naught is the same as A naught or B naught. So De Morgan can be applied here, so I will have X naught dot, instead of or, is and then Y dot Z naught. So what I use is De Morgan. It looks like I could use De Morgan again in this parentheses. It's X naught or it will be Y naught plus Z naught. And if I use distribution, that's what exactly I have here. And we're done. So the next one we say is true by duality. Or you could prove this one here in blue and say that this one is true by duality. And to prove this, we're going to use De Morgan here. So the dots become plus, and again the dot plus become dot, and we end up here. Let's see this example. We'll maybe start with the left hand side, and we're going to use distribution. So it's x plus y dot y and x plus y dot 1. So it's x plus y dot y plus x plus y dot 1. So the next thing I would use is, looks like commutative law first, 1b, and then I'm going to use distribution. And now idempotent x dot x is just x. So what I'm going to use is idempotent. At the same time, we'll stop and think what I need. I need the x, which I have. I need x dot y, which I have. But this one here, instead of x plus y dot 1, I need just y. How you get there? So if we use idempotent and the 4b, the identity, we end up with x dot x is just x and x plus y dot 1 is just x plus y. You could write it in 2 steps, but right here to save space, I write it in 1 step. So next we're going to use commutative. So let's put the xy here first, then here is x plus a, commutative law. I flip this too. And now, if I use the associative law, I will end up with x plus y. What I use is 2a. And now we know that x plus x is x, because if idempotent, and then plus y plus xy. And the next thing, I'm going to rearrange it as we want it, which is x plus x dot y plus y. So all what I did is, again, commutative law, which is 1a. And this one here, I would say true by duality. So this is one way of proving this. Here in blue, I would write another method of proving this. So I see that the first thing I will do is to use distribution property, which is x, and then y plus y dot 1. And then the next one, I see that I could say instead of 1, because I'm missing x, so what I'm going to call 1. 1, it could be x plus 1 by using the universal bound. And then if I use distribution, which is 3b, we get this. And then we have x plus, instead of yx, I need xy. So let me flip it now. What I use is 2a. Okay, we know that y dot 1 is just y because of 4b. So I get x plus x dot y plus just y. And we're done. This is the other side. So sometimes there is more than one way of getting to the other side. So here I showed two proofs for the same expression. We'll stop here and we'll continue in the next video with more proofs.